Good morning. We are ready to move on into Chapter 14. We're going to start looking in Chapter 14 at oscillatory motion. So that is the plan. So for oscillatory motion, we're really looking at anything that oscillates back and forth. And they've got this example of the car's suspension system. You know, if you hit a bump, then you've got springs or shock absorbers to be able to initially allow for a little bit of oscillation and then have that damp out quickly. And so let's take a look at something simpler than that picture. Let's go back to a very easy example, and that would be an object with some mass attached to a spring, and the spring has some kind of a spring constant. So there is some kind of a spring constant K, little k, that goes along with this spring that tells us the spring property. Now when we have a spring attached to something, to an object with mass, there's an equilibrium position, and what we typically do, almost always, 99.9% of the time, is we set the coordinate system up so that x equals 0 corresponds to the equilibrium length of the spring. So, and then what will happen is, if we pull the object away from equilibrium, the spring brings it back. And we, earlier when we looked at springs, we listed this force as the force is equal to minus kx. So if x is in the positive direction, the force is in the negative direction. If x is in the negative direction, the force is in the positive direction. Now for an ideal spring, this restoring force, is what we call it, is proportional to the displacement. So that's kind of where we're headed. Now it says this, it says we assume that the surface is frictionless. We don't have to do that. I just wanted to point out we can think of it as having some friction. We're going to start off with no friction to keep things simple. And then there's going to be a point where the spring is at its natural length, at equilibrium. We set that location to be x equals 0. And then the force, the restoring force, is minus k times x. Now notice that we're setting up the mathematics in a way where we can check and make sure that x and f are being correctly represented with that minus sign in place. Now the minus sign, they're saying, tells us it's a restoring force, and it will always be, a force will always be opposite the direction of the displacement. K is the spring constant, we've seen that before. The force in this case is not constant. We can't use formulas of constant acceleration. I know that's a set of formulas that we developed back in Chapter 2, but we're in this oscillatory motion, it's not going to apply. So we have to rederive what will the motion look like for this situation. Now we still use this. So our starting point for oscillatory motion is to go back and write down the acceleration at any instant is given by the force divided through by the mass. All right, now as this thing oscillates back and forth, the displacement is going to be x. That's measuring our distance from the equilibrium point. So the equilibrium point is designated to be x equals 0, and then as this oscillates back and forth, x is going to vary. Now the largest displacement is called the amplitude. So the amplitude, the object here is oscillating back and forth between maximum displacement in one direction, maximum displacement in the other direction. If the spring constant is truly a constant, there's just that one k value, then the amplitudes in each direction will match. And the object will oscillate back and forth between plus a and minus a on the scale. Now, what they're showing here is if we start out from rest and then we let go, the force of the spring is going to cause this to increase in speed. It's going to pick up speed all the way to the equilibrium point. Once it crosses equilibrium, it's going to begin slowing down because the spring now is trying to pull it back to equilibrium. It's kind of like the spring goes, hey, get back to equilibrium right now. I'm going to push you there. But then the spring pushes too hard and pushes the object past equilibrium and goes, oh no, now I got to bring the object back to equilibrium, but then it overshoots again. And so if there's no friction, then this oscillation just goes on forever. Now in reality, there's going to almost always be something that slows the system down. But for now, we're going to treat this ideally as it continues to oscillate back and forth between A and minus A. Now, where is this thing traveling the fastest? And that would be right as it passes equilibrium. So right as it passes equilibrium, that's the highest speed. Once it passes, it begins to slow down. So it's a good set of diagrams to study. Go through and take a look. So we've identified displacement and amplitude. A cycle corresponds to all of the motion back and forth, completing one trip, and then you just keep repeating that cycle over and over. If you've seen one cycle, you've seen them all. All the cycles look the same for the example at hand. Now the period is the time required to complete one cycle. So how long are these cycles taking? And that's referred to as a period. The frequency, which is the inverse of the period, is the number of cycles completed each second. Okay, so there's a fair amount of vocabulary we're going to develop in this chapter. All right, what happens if, instead of a horizontal frictionless surface, what if we hang the object from a spring and let it oscillate vertically? Well, it turns out hanging the spring vertically, the effect overall is to just adjust the equilibrium point. Now, instead of the equilibrium point corresponding to the spring not being stretched out, the spring is stretched out at equilibrium. So we can say that at the equilibrium point, there's a gravitational force downwards. There is a force of the spring. Now the force of the spring is going to be K x naught, where x naught represents a positive number, a positive difference, and it's in this direction. So x now is going to be measured from here. This is the equilibrium point for the oscillations. So hanging it vertically, it turns out, for an ideal spring doesn't change the formulas. It just resets the equilibrium point. Now I went into a little more detail. So here is the spring when we first hung the spring, and then we attached it and brought it carefully to equilibrium. So it's not moving. There is no acceleration, no velocity. These two forces match, and that says the distance that it stretches is given by mg over k. That will determine where the new equilibrium point will be. So now we're going to take that new equilibrium point, call that, we're going to designate that as x equals 0, and then we're going to let oscillations take place surrounding the new equilibrium. So now the amplitudes will be evenly spaced around the new equilibrium level. And then these formulas are just saying, well, the net force acting on this now, the net force is minus k x naught plus x. Eventually we are able to go in and show that kx naught is equal to mg, and that says that with the new set of formulas, the minus k naught, the minus kx naught cancels the mg, and the f net ends up looking like it did originally. So the gravitational effects cancel out in terms of the new equilibrium position. So that's good to know. If you get a vertical problem, you don't have to rethink everything. The original set of formulas will work. Now here's a set of car springs. This is kind of like, oh, they went into, showed a lot more detail. There's the brakes and everything. So it says that we have a car, and that a family of 4 with a total mass of 200 kilograms climb into their 1,200 kilogram car, and the car compresses. You know, and when you get in your car, it's a little lower. The suspension compresses a little bit. And then it says, what is the spring constant of the car's springs, assuming they act as one combined spring. So we can set that up. And then it says, what happens if we take some additional luggage? What if we load the car with an additional 100 kilograms? What's going to happen? So here we go again. Here is the spring, just the spring by itself. And then what we're going to do is we're going to set the car on the spring. Now that's like taking M1, the mass of the car, and setting it on the spring. That's going to compress it. So what happens is K times X1, so X1 represents the distance that the spring is compressed, is equal to M1G. Now when we add some additional mass, here's some more mass inside, now we have M1 plus M2, and the spring is going to compress even more. So in the first picture, we have K times X1 equals M1G. In the second picture, at equilibrium, Kx2 is equal to M1 plus M2 times G. We can take the first equation, subtract it from the second equation, and that's what we end up with. We end up with K. See if we've picked it up. We have right here. So X2 minus X1, we were told, is 3 centimeters, or 0.030 meters. And then solving that lower equation, K is equal to M2G, the difference, just the additional amount, over X2 minus X1. So the Ks can be calculated just by knowing how much additional compression occurs with the additional mass. We don't have to do this. We don't have to go back and remove the car from the springs. We can start with the car, the spring's already compressed, and then just see how much additional compression we end up with. That's enough to go through and solve this. Now, putting all the numbers in, ended up with a K value for the entire suspension system at 65,300 newtons. Now, that says that X can be calculated as the force divided by K. So let's see how the compression took place. So using this formula, using mg over K, I can start out with the mass of the car itself. So now I realize, oh, the mass of the car itself compresses the spring 18 centimeters. So before anybody got in the car, the springs were already compressed a lot, 18 centimeters. When the 4 passengers came in, that added 200 kilograms. That compressed it to 21 centimeters. That's why we observed a 3 centimeter compression. If they take along 100 kilograms of luggage, that's going to compress. I just keep putting these different mass values into that formula. That compresses it to 22.5. That gives us an additional 1.5 centimeters of compression. So you can see what's happening as we load the springs. Now, for any oscillating system where we have a restoring force proportional to the displacement, this results in simple harmonic motion, where the word harmonic means it indicates a cosine or a sine function. Now, I'm hoping, I'm guessing, in your math classes you've worked with sine and cosine functions a lot. They're very useful, and they certainly are going to be useful for us now that we're looking at something that oscillates. So a sine or a cosine function can be set up to represent oscillations in time. And that's what we want to use them for. So the simple harmonic motion, sometimes this is referred to as a simple harmonic oscillator. I wish they would take out the word simple, because it's not that simple. It's actually a little complicated. But what they're referring to is, this is the simplest type of oscillation that we can come up with. It's the simplest force relationship, is to say F equals Kx, and k is a constant, and the solutions turn out to be sine and cosine functions. Not all oscillations are sines and cosines. That's not the case. But for this particular type of restoring force, that's what we end up with. Now, what they've got here, don't panic about this stuff. This is the acceleration, and they're saying that when we take this force, we end up with a formula that says the acceleration plus k over m times x equals 0, where x is a function. Let's see where that comes from. And it comes from here. So for oscillations, we're going to say the acceleration is equal to f over m. Now the force we're dealing with is an oscillatory type force. It's a restoring force where f is equal to minus k times x. So I can take that and substitute it in and say the acceleration depends on displacement. The larger the displacement is, the larger the acceleration will be. Now, k and m are constants. Acceleration and x are functions of time. So don't be fooled by this equation. X and a are these functions that are fairly complex. K and m are just constants. So if I take these functions and I can do this, I can say that the acceleration is the second time derivative of the x function. That gives me a differential equation, and that's what they're showing. Now, the solution to this is a sine or cosine. Let's see how that works. Let's say that for our displacement function, we're going to say that's a cosine of omega t. That means the velocity is the first derivative. So the first derivative will be minus omega a sine omega t, and that tells us how the velocity is changing. Now notice, sines and cosines are what we call out of phase with each other. And what that indicates is when the displacement is the largest, the velocity is 0. Well, that makes sense. If I've got something oscillating back and forth, at the extremes, the object momentarily is stopped. Just for an instant, v equals 0. Now, when we're at the equilibrium point, when x equals 0, the velocity is going to be at its highest value. So if this is a cosine, this is going to get represented as a sine. Now the acceleration is one more time derivative, and that means that the acceleration is going to be represented by a cosine function, and that matches with the displacement. So the acceleration is a cosine function. More specifically, it's a minus cosine function. So in some sense, it's exactly opposite the displacement. Now, that's what we need, right? Because what we said was the acceleration is going to follow the force, and the force needs to be opposite the displacement. So there's a minus sign in my formula. When I take two derivatives, I need to get the function back again, and there need to be some constants out front. Well, that's how this works. What I end up with is a couple constants over here, omega squared, and that tells me that the frequency, omega squared, is going to be k over m. So omega represents the frequency of oscillation. Now, we've worked with omega before. So we've seen omega as an angular velocity for rotations. Now omega is going to be keeping track of how the oscillations are taking place. So as you oscillate back and forth, omega is going to be the rate, the frequency at which those oscillations occur. And by looking at the formulas that we've gone through, we know how to determine what the frequency will be. If the k value is large, if it's a very stiff spring, that makes the frequency faster. If there's a lot of mass, that slows the oscillations down. Okay, so here is a vertical spring, and here it is oscillating back and forth. and they've got this paper that is scrolling by, and what we're saying is that the sine function or cosine is going to get drawn out along that piece of paper, because the horizontal axis becomes a time axis. Now this is a cosine function. It starts right at A, and then here it is mapping out the cycles. The oscillations are taking place around the equilibrium point, and they go up to positive A, and they go as far down as negative A. Now, the solutions that the textbook's using, in addition to the omega t, they're putting in this extra phase angle. What that indicates is that, so for example, right here, that's a sine function. So this motion is being represented as a sine function. We start off when the object's at equilibrium. This one's shifted a little bit. And so putting in a phase angle allows us to mathematically represent a function that's shifted a little bit. We're not going to worry about that. Just be aware when you see those angles written that way in the textbook, that's what they represent. All right, let's see. Omega is can be represented as 2 pi f, where f is the frequency, and that's going to be equal to the square root of k over m. The omega is going to be in units of radians. Now, if we work in terms of frequency, that's going to be omega divided by 2 pi, and that's going to be in hertz, which indicates cycles per second. And then finally, the period of the oscillations is going to be 2 pi divided by omega, and that's going to be in seconds per cycle, or more commonly, it's just listed in terms of seconds. Back to the car springs. So what will be the frequency of oscillations for these car springs? What we're assuming is that the shock absorbers are completely worn out, and when you hit a bump, the car oscillates, and it just oscillates forever. Not a good suspension system. So the car hits a bump and you begin to oscillate. What will the frequency of those oscillations be? So here's the car again. The frequency of oscillations we determined would be k divided by m square root. The k value we calculated was 65,000 newtons per meter. The car loaded with the four passengers is 1,400 kilograms. Take a square root. It says that this car will oscillate at 6.81 radians per second. Now that's useful for mathematical formulas and such, but something that's more intuitive is to write this as a frequency or as a period. So let's write it as a cycles frequency. Omega over 2 pi gives us 1.08 cycles per second, or 1.08 hertz. That's about one oscillation every second. It's very close to one oscillation every second. So that's kind of like, you know, something like this. 1, 2, 3, maybe a little faster. 4, 5, 6, 7. So that's a pretty good oscillation rate or frequency. The period is 0.9 seconds. So it actually oscillates once every 0.92 seconds. Okay, that would be annoying if the car kept oscillating forever like that. Now, we already went through and looked at this. We said that if we use a cosine to represent displacements, then the velocity is a negative sine, and the acceleration is a negative cosine. The Vmax is, we'll have to see, the Vmax is going to be given by omega A. Whatever is out front of this sine function will tell us what the maximum value will be. The maximum accelerations are going to be omega squared times A. And they're drawing these with no phase angle at all. So kind of like what we're going to be looking at. All right, so you can see that when we first start out, we're at maximum amplitude. The velocity is 0 at that instant, and the force, the acceleration, is bringing us back to equilibrium. So these two are good to kind kind of stare at. Now what I did was I highlighted one cycle. So it's fine to see that this is going to continue on, but by highlighting one cycle, you can say, okay, if I've seen one cycle, I've seen them all. Because every cycle, in this case, with no damping taking place, no frictional forces, no air resistance, it's just going to keep oscillating with the same amplitude. Okay. And breaking it down, I should say this too, this is the time axis, this is one period, so it's very convenient to break this down into 4 regions. Each one of those is made up by 1/4 of a period. And so during the first fourth of a period, the object travels back to equilibrium, the next fourth takes it to the opposite extreme, another fourth brings it back, and then another fourth brings it back to the original location. All right, here's another example. This time it's a vibrating floor. So it says that we have a factory, and for whatever reason we need a floor that vibrates. It needs to be a frequency of 10 hertz. Wow. So that's, I can't oscillate my hands that fast. So I got to get 10 cycles per second of oscillations taking place. And the amplitude of the motion is 3 millimeters. So I got to go back and forth 3 millimeters 10 times a second. I got to complete 10 cycles. So let's see what that looks like. Well, I'm going to go back and use a cosine for my displacements. I'll use a negative sign for the velocities and a negative cosine for the accelerations. These coefficients out front are telling me the maximum displacement is A, the maximum velocity is omega A, and the maximum acceleration is omega squared times A. So those are the max values. The amplitude is 3 millimeters. The frequency was given as 10 hertz. I've got to get that converted into omega. And so omega here is going to be 62.8 radians per second. So that gives us an X max of 3 millimeters. That was given. V max, I multiply by omega. That says 188 millimeters per second. Now 188 millimeters, that's like 18.8 centimeters. And then finally the acceleration, after I multiply by omega, that's 11,840 millimeters per second. I converted that into meters, and it's 11.8 meters per second. So that's a pretty large acceleration that the floor is undergoing. So, and that's what we find with oscillations. So even though the amplitude wasn't very large, the frequency was pretty good sized. And that led to some really large accelerations for this factory floor. Okay, another very similar example here is with a loudspeaker. So we've got a speaker set up here, and the diaphragm in the speaker oscillates back and forth, and we use that to generate sound in the air. So mechanically, or using magnetic forces, we can oscillate the speaker diaphragm back and forth. Now it says here we're going to have a frequency of 262 hertz. That's middle C on, you know, the piano or whatever, some musical instrument. The amplitude of these oscillations is tiny. So the amplitude here is 1.5, 10 to the minus 4. Now, when we get to the chapter on sound, you'll see that a displacement of 1.5, 10 to the minus 4 meters is enormous. This is going to be a really, really loud sound. Stand back away from the speaker. So this diaphragm is oscillating back and forth 262 times a second at this amplitude. What equation should we use? What are the velocities and accelerations? What's the position of the cone? So let's do this. I'm going to go back, and I'm just going to keep using these same formulas until they tell me not to. So displacement, velocity, acceleration. Again, the X max, the V max, and the A max. Now this time, the amplitude is 0.15 millimeters. So it's just a tiny fraction of a millimeter. The speed, though, the maximum speed, 24.7 centimeters per second. The acceleration is pretty large. It's got an acceleration of 406 meters per second squared. As this thing oscillates back and forth, the acceleration is really, really large. Now, in addition to the, I guess we had to calculate this, right? So the frequency was 262. That made omega 1646 radians per second. And, you know, just to throw this in, what was the period? Well, the period of oscillations is 3.8 milliseconds. 3.8, 10 to the minus 3 seconds, and that's what one cycle looks like. So I graphed it and said this is my unit cycle, that represents one cycle, and that's the period. What they asked about was, where in the cycle will this be at the 1 millisecond mark? So if we start the cycle here at maximum amplitude, and the entire cycle is 3.8 milliseconds, that says that 1 millisecond is probably just a little beyond that first equilibrium point. So I'm guessing we're here. So at 1 millisecond, I'm guessing the displacement is just a little bit negative. And so let's try it. This was the formula, keeping track of displacements. I need to calculate omega t, and I need to make sure my calculator is set for radians. So one of the easiest errors to make, one of the most frustrating errors that show up is not remembering to convert between degrees and radians. So what's going to happen is that the omega t is going to come out in radians. The omega is 1646 radians per second. We're looking at 1 millisecond. The seconds cancel. 1.646 is in radians. I got to convert my calculator to make sure it knows the number I'm giving it is in radians. Now the cosine function at that point is minus 0.0751. Plugging that back in with the amplitude, we end up with, at that point, we are at 0.0113 millimeters. So yeah, that diagram that we made back here suggested to us that a 1 millisecond compared with 3.82, 1 millisecond was going to be just over here somewhere, just beyond that 0 point, and it's going to be a little bit negative, and that's what we got. Now, in addition, the velocity here at that point is negative, so it's minus 24.7 centimeters per second. And we go, yeah, that's true too. Not only are we at negative x values, but we're headed in the negative direction. Now, the acceleration is in the positive direction. So again, if this is describing what's going on, by the time I get to this point, I'm at a negative displacement, I'm headed in the negative direction, but the acceleration is going to be positive. The acceleration is now trying to bring me back to equilibrium. So the numbers look fine. The numbers look like what we might expect. Okay, that's encouraging. All right. Ooh, here is another problem. I guess we can look at all of this. This is an example of what homework problems might look like. What we've got is we've got a spring attached to something. That something is 300 grams, and the spring is, it tells us the spring stretches 15 centimeters when a 300 gram object is, okay, it calls it gently attached. So that, I'm going to say, could be kind of confusing. I kind of wish they hadn't described it that way. In any case, here is the spring, and here is the mass that we attached. And what we've got is Kx naught is equal to mg K is equal to mg over x naught. And that says a 300 kilogram, not 300 kilogram, 300 gram object times g divided by the amount that it's stretched gives us a K value of 19.6. So I've got a K value of 19.6 newtons per meter. And here's the horizontal case. Here it is oscillating back and forth horizontally. So what they tell us is, okay, now that we've determined this, we could either oscillate it here, or we could set it into oscillation there. It doesn't make any difference. Now we've determined the K value. What was it they specifically asked us to do? Yeah, so they did. They moved it. They didn't have to, but they did. So anyway, we're now looking at this picture, which is going to behave the same way. So this is telling us that we set it into motion, and we set it into motion by pulling it back 10 centimeters and letting go. Now, if I pull this back 10 centimeters and let go, the amplitude is 10 centimeters. So it's going to oscillate back and forth between 10 centimeters in this direction, 10 centimeters back in the other direction. It's just going to oscillate back and forth, right? And if everything is truly frictionless and no air resistance, then the amplitude will remain 10 centimeters. Now the Vmax is omega times A, and we can now calculate the omega as K over m square root. So the omega, 19.6 newtons per meter, divided by 0.30 kilograms square root, the omega is, now that's a little hard to see. There is a decimal. The omega is 8.083. So make sure that's a decimal. It's not a comma. All right, and that's in radians per second. All right, Vmax then is omega times the amplitude. That gives us a maximum speed, 80.8 centimeters per second. Okay, the maximum acceleration, part A, B, C, D, E, F, G, that's a lot of parts. The maximum acceleration, omega squared times A, well, put another factor of omega in, that works out to be 6.53 meters per second squared. All right, and then the frequency in hertz would be the radiance frequency divided by 2 pi. And that gives us again, that's a decimal, 1.229 cycles per second, and that is 1.29 hertz. The period is the inverse. That's 0.777 seconds is what I calculated. And then what are the formulas representing this? We can use our old friend cosine and negative sine. Those work fine. Nothing, I don't think, anything they told us that requires us to use a different function. Okay, so displacement is a function of time. All right. And then let's take these two equations from F and G, and then we want to plug in this number. Time is equal to 0.150 seconds. When I do that, and I put in the omegas, and I set my calculator to radians, I end up with a displacement 3.51 and a velocity negative 75.7. Let's see if we can make sense of that. See if those numbers seem reasonable. What was the period again? So the period is 0.777, and the time we're looking at is 0.15. So 0.15 would still be in the first quarter of the cycle. So for the cosine function, we don't have it listed there, but we've got one here. So I'm going to go back and use this diagram. The entire period here was 0.777, and 0.15 would put us here. So if I'm here, the displacement's positive, the velocity is negative, and the acceleration should be negative. Let's see what we've ended up with. The displacement is positive, the velocity is negative. They didn't actually ask about the acceleration, but that seems plausible. You know, the maximum acceleration, the maximum velocity is at the center, 88.8, and what was the displacement? It was 10 centimeters. And so we're most of the way back, and that means that we're getting close to maximum velocity. All right. So, you know, my recommendation is do the math, but have a function, have the oscillatory functions, the sines and cosine diagrams right next to you so you can compare numbers when you're doing these calculations. And, you know, and don't panic if the problem has parts A, B, C, D, E, F, G. That's just what happens sometimes with these examples. Okay, now I think this is a, let's move on from this. Yeah, okay. That's a slide shouldn't be in there. I'll have to make sure I get that taken out. All right, let's move on to the next portion of this chapter. And what we're going to be looking at here is energy. So we've been looking at the kinematics of oscillation. So we've spent a good amount of time here looking at how the kinematics work. What about energy? There clearly is kinetic energy and potential energy, both, in these oscillations. So if we start off here, this is kind of the same set of pictures we've been looking at. If we start out with the object pulled back some amplitude, and then we let go at that point, then we're going to have energy, potential energy, 1/2 Ka squared when we start. Now, right as we pass equilibrium, all of the energy will be kinetic. So it's going to go from all potential and then gradually shift until the point where it's all kinetic. And then by the time it gets back out here again, now it's all potential. So with oscillating objects, we're going to have the energy switch back and forth between being potential and kinetic. Now in general, if we just pick some kind of a random location right there, the potential energy is going to be 1/2 Kx squared, and the kinetic energy will be 1/2 mv squared. So most of the time, the energy is being shared. At very specific points, the energy is totally potential or totally kinetic. All right, the total energy that we have for these oscillations, the total energy would be 1/2 Ka squared. That's what we saw. Now, that means that at any point during the oscillation, the combined kinetic and potential energies are going to equal the total energy, and that means that we can write down the velocity as a function of position. Now, these formulas certainly work. I don't use them that often, but they are introduced in the textbook, and so it does provide a way. If they tell you the location of the object, you can calculate how fast it's going at that particular time. Now here we've got a graph. The vertical axis is energy. The horizontal axis is displacement. And so what we've got is this object is going back and forth between negative A and positive A. So those are the extreme values for the displacements. And at all times, the kinetic energy and potential energy combined, which we're calling E, is 1/2 Ka squared. So there's a fixed amount of energy here. Now, the graph that they've drawn, the red line, that they've drawn is the function 1/2 kx squared. That's the potential energy. So let's pick a random point. Let's say that we're right here in the oscillations. If I am right here in the oscillations, then this represents the potential energy at that time, and the remainder will be kinetic. So out here at full amplitude, it's all potential. But in here at the equilibrium point, it's all kinetic. So the red line divides the energy up into which portion is potential and which portion is kinetic energy. All right, I think we're getting to a point where we may want to take a break. Let's take a quick look. Oh no, we've got a few minutes here, so let's move ahead and say a few more things. So here are some, here's an example of doing some energy calculations. Now it sounds like we may be looking back at a previous example. The K value looks familiar. There's a K value of 19.6 newtons per meter. Now the amplitude is 10 centimeters. Yeah, this is sounding familiar. We're going to start, we're going to write the x. Oh, we're starting from the negative amplitude. Okay, so we're going to start off at a negative 10 centimeters. And we're going to be using a cosine function. That is omega. So I don't know if we've discussed this before, but I always feel like writing these formulas with numbers in them is, to me, it's confusing. I feel like it's more useful to write the formulas in terms of variables and then just write down what the variables correspond to. Now, this is the velocity function. Now again, they're using the Greek letter nu. They really keep switching back and forth. Let's see. The total energy function. Okay, I hope I've read this carefully. Let's see if we can get all of this answered. First of all, let's take a look at oscillation energy. Ooh, I hope I spelled energy correctly. Let's take a look at oscillation energy. There's potential energy. That is 1/2 kx squared. Now, x we've been writing as a cosine omega t. Well, I can square that. And what that says is the potential energy as a function of time is 1/2 ka squared. That's the total energy, times the cosine squared function. Now, you guys remember what cosine squared functions look like and sine squared functions? So we may have to go back and review that just a bit. Anyway, let's get some more stuff in place here. This is the kinetic energy at any instant, 1/2 mv squared. Well, if I'm using a cosine omega t to tell me the displacement, then the velocity will be minus omega a sine omega t. Now this is squared, so I didn't bother writing the minus sign. But what this gives me is a bunch of coefficients out front, 1/2 m omega squared, a squared, times the sine of omega t squared. Now, m omega squared, that's the same thing as k. So this coefficient out front matches this one. So the total energy could be written as the maximum potential. Now the maximum potential energy is 1/2 ka squared. The total energy could be maximum potential or maximum kinetic. They can both be represented as 1/2 ka squared. So let's calculate those numbers. Yes. So, yeah, I guess this is just a restatement. The maximum kinetic energy, 1/2 m v max squared, which gives us 1/2 m omega squared a squared, which is right there. So let's start running through the parts of the problem. We got this stuff set up that we needed. The total energy of oscillation is 1/2 Ka squared. I put everything in standard units, multiplied them out, and found out that the energy of oscillation is 98 millijoules. 98 millijoules. So it's about 1/10 of a joule. That's not very impressive. That's not an enormous amount of energy. The kinetic energy then can be written as total energy sine omega t squared. The potential energy can be written as total energy cosine omega t squared. Now, as you guys know, if you take a sine squared and a cosine squared and add them together, you get 1. And so that's what's happening in terms of the energy. As time progresses, the total energy remains constant, but it shifts back and forth between being kinetic or being potential. Now, the mass of this object is 300 grams. They are asking in part C, let's take a look at this. What will the velocity be when the object is 5 centimeters from the equilibrium position? And so what we can do for that is we can set x equal to 0.050 meters, and what we find is the potential energy at that instant is 24.5 millijoules. Well, if the total energy is 98 and the potential energy is at 24.5, that means the kinetic energy at that instant is going to be total energy minus potential. That's going to be 73.5. And so the velocity then will be given by 2 times k divided by m square root, and that says how fast we're moving. So in this case, we've used energy conservation to calculate our numbers. So we can work back and forth using total energy as a way to approach the problem. Now, in the very last part of the question, part D, it says when the amplitude is when the displacement is 1/2 of the amplitude, how are the energies divided up? And the potential energy then would be 1/2 kx squared, where x is equal to 1/2 a. Bringing out those factors of 1/2 gives me a 1/4 times 1/2 ka squared. It says that would then be, it would be 1/4 of the total energy. When the amplitude is, when the displacement is at half amplitude, 1/4 of the energy is potential, and that says that the kinetic energy must be the remaining 3/4. This is how the energy would be divided up. Now, if you think about it, 5 centimeters is the half amplitude. They ask us kind of the same question in part C and in part D. All right, so I think that's a good time. Let's go ahead and take a break. Let's move ahead here and see where we're headed. There's an example that we'll start off with. But let's go ahead and stop there. If you guys have questions, let me know.